Okay, good morning. In this video, we will delve into a detailed explanation of additive manufacturing. Additive manufacturing, also known as 3D printing, is an innovative technology that creates three-dimensional objects by adding layers upon layers of materials such as plastic, metal, or even living cells. We will discuss the capabilities of additive manufacturing in terms of geometric and material properties. Geometric capabilities refer to the shapes and sizes that can be produced by the technology. Additive manufacturing technology allows for the production of highly complex and intricate shapes which would be impossible to manufacture using traditional manufacturing methods. Material capabilities refer to the range of materials that can be used in additive manufacturing. The technology can work with a wide variety of materials such as thermoplastics, metals, ceramics, and even biological materials. Furthermore, additive manufacturing allows for the creation of new materials that are not possible with traditional manufacturing methods. Additionally, we will explore the classification of additive manufacturing based on ASTM standards and the type of raw stock material used. ASTM standards classify additive manufacturing technologies into 7 categories based on the type of energy source used, the process, and the materials used. We will also discuss how additive manufacturing can be classified based on the type of raw stock material used, such as powder bed fusion, material jetting, and sheet lamination. By the end of this video, you will have a solid understanding of additive manufacturing, its capabilities, and its classification, which will help you make informed decisions when choosing the best technology for your specific needs. The technology of 3D printing is a manufacturing process that involves creating a three-dimensional object from a digital file. It is also known as additive manufacturing as it adds successive layers of material until the desired shape is achieved. There are several terms associated with this technology, each of which refers to a specific aspect of the process. Stereolithography, for instance, is a type of 3D printing that uses a laser to solidify a liquid resin, creating a solid object layer by layer. Additive layer manufacturing, on the other hand, refers to the process of adding material layer by layer until the object is complete. Similarly, solid freeform fabrication involves creating a three-dimensional object from a digital model by depositing successive layers of material. Digital manufacturing is another term used to describe 3D printing. It involves using computer-aided design software to create a digital model of the object and then using a 3D printer to produce it. Rapid prototyping is a term used to describe the process of quickly creating a prototype of a product in order to test its design. Rapid tooling is another term associated with 3D printing, and it refers to the process of using 3D printing to create molds and other tooling components. Overall, 3D printing is a versatile technology with a variety of terms associated with it, each of which describes a specific aspect of the process. As we shown in the figure, we can see there is the difference between subtractive manufacturing and additive manufacturing. So we can, in the case of additive manufacturing, we will start from nothing and we will gradually add layer by layer and finally we will get the desired product. But in the case of subtractive manufacturing, for example, CNC drilling machine or lathe machine or milling machine, we will start with a block of metal and we will use a particular tool to remove material from the workpiece, and we are using chuck to hold the workpiece. And finally, material is removed with the help of hard tool and we will get the final product. But in the case of additive manufacturing, we will start from nothing. We will use the material and finally we will get the desired product. Next is, what is the difference between 3D printing versus 2D printing? 3D printing and 2D printing are the two different printing methods. The former involves creating a three-dimensional object from a digital model, while the latter involves printing two-dimensional images onto a paper or other flat surfaces. With 3D printing, a physical object is created by adding material layer by layer based on a digital design file, also known as computer-aided design data. This process allows for the creation of complex shapes and designs that may not be possible with traditional manufacturing techniques. Additionally, 3D printing can use a variety of materials, including plastics, metals, and even living tissues. On the other hand, 2D printing is typically used for printing text, graphics, and images on paper or other media. So, uh, from this image, we can see what is the difference between a 3D printer and a 2D printer. With this image, it is very clear. So this figure is representing Ultimaker machine. This white machine is Ultimaker machine, and this is the 2D printer. This is the right side is representing the 3D printed of the 3D printing of Eiffel Tower, and this figure is representing the 2D image or 2D printing of the Eiffel Tower on a paper, and this is representing the 3D printing of Eiffel Tower using PLA material or ABS material using Ultimaker 3D printer machine. Then coming to the definition of additive manufacturing process. Additive manufacturing is a revolutionary manufacturing process that allows for the creation of three-dimensional physical models directly from CAD models. This process is fully automatic and does not require the use of cutters, tools, or fixtures specific to the object geometry. Additive manufacturing is an incredibly versatile technology that can be used to fabricate a wide range of objects, including parts, prototypes, tools, and even assemblies. The process of additive manufacturing involves three primary steps: pre-processing, building the part, and post-processing. The first step is pre-processing, where the digital CAD file is prepared for the additive manufacturing process. During this step, the file is tessellated, sliced into layers, and support structures are generated. The next step is building the part itself. This step involves the use of additive or stocking methods to build up the part layer by layer. Additive manufacturing works by depositing layer upon layer of material, which is fused together to form the final object. The process is highly precise and can create objects with complex geometries and intricate details. Finally, the post-processing step involves removing the support structures and performing any finishing operations on the final object. This may include sanding, polishing, or painting. Additive manufacturing is a highly flexible and efficient process that has revolutionized the manufacturing industry. It allows for the creation of highly complex objects with a high degree of accuracy and precision. The technology is rapidly advancing, and its use is becoming more widespread in industries such as aerospace, medical, and automotive. Then, next is we will enter into the staircase effect. When it comes to 3D printing, it is important to understand the layer by layer technique that is used to create objects. In the figure, you can see the first figure, you can see the layer. There are three images you can see, and the layer thickness are different. The last figure is representing with minimum layer thickness, and the first figure, this figure, is representing the 3D printed object with a maximum layer thickness. That this technique involves the gradual layering of material to create the desired shape of the object. However, one downside of this method is the visible staircase pattern that appears on the surface of the printed object. This pattern is caused by the slight offset. So in this figure, you can see there is a slight offset between each printed layer, which becomes more pronounced on surfaces with curves or oblique angles. The greater the variation in the curvature of the object, the more noticeable the staircase effect becomes. It is important to note that this effect can be minimized by adjusting the printing parameters such as the layer thickness and printing speed. By adjusting the layer thickness like this and the printing speed, as well as by using specialized software, we can reduce this effect, this staircase effect that can compensate for variations in the object's shape. Then next is we will enter into the different steps involved in the additive manufacturing process. See, I am directly using some files from the Google. Why? Because is that if anyone is interested in further researching about the topic, you can directly Google it, because I am using the documents from the Google, and I am using the relevant files, relevant images to explain the concept. Okay, so this is from ResearchGate. Okay, so next is the different steps involved in additive manufacturing process. So additive manufacturing, commonly known as 3D printing, I already explained that it is a process of creating physical objects by adding material layer by layer. The first step in additive manufacturing is to prepare a CAD model, computer-aided design model of the object that is to be printed with the help of any software such as Autodesk Inventor Professional, Fusion 360, SolidWorks, or any other dedicated software. The first step is to prepare the digital file. This can be done using solid modeling, digitizing, or scanning techniques. Either we can use solid modeling or we can use digitizing or scanning techniques. The CAD model is a virtual representation of the final physical part, and it is essential to ensure that it is precise and accurate. Once the CAD model is ready, it is converted into an STL format. STL means stereolithography format. What is STL format? The STL file is a triangular mesh that approximates the surface of the object. It is necessary to ensure that the STL file is error-free to avoid any issues during the printing process. If there are any errors in the STL file, dedicated software can be used to manipulate the file and make the necessary corrections. The next step is to generate the support structure for the object. In the physical in the file we are going to print, suppose if there are some overhanging features, we have to give we have to generate support structures. Why? When we are adding materials, because of the gravitational force, if support structure is not there, the material will not we will not get a proper shape because of the absence of the support structure. So it is very important that we should generate proper support structure for the object. The support structure acts as a foundation for the object during the printing process and is necessary to ensure that the object is stable and does not collapse. The build orientation is also selected at this stage. The build orientation is also very important. If the build orientation is wrong, then we have to provide more support structures. But by the proper selection of the build orientation, we can remove the use of the support structures. The build orientation determines how the object will be printed and can affect its strength and stability. After the support structure and build orientation are set, the file is sliced into appropriate layers using suitable software. With the help of suitable softwares such as Ultimaker Cura or Idea Maker or Reptile Host. Reptile Host is a dedicated application for artillery sidewinder software. Sorry, artillery sidewinder 3D printing machine. Ultimaker Cura is a dedicated software from the company named Ultimaker. Who are those who are making the machines named Ultimaker S5, S3, S7, etc. etc. Each layer is a cross section of the object and is printed one at a time. The sliced file is then uploaded into the 3D printer and the printing process begins. Once the printing process is complete, the object is removed from the printer and subjected to post-processing operations. This involves removing the support structure and any excess material that may have accumulated during the printing process. The final physical product is then delivered to the customer. So in summary, the additive manufacturing is a complex process that involves several steps including CAD modeling, STL conversion, support structure generation, build orientation selection, slicing, printing, and post-processing. Each step is crucial and requires careful consideration to ensure that the final product is of highest quality. Then coming to the STL file. What is STL file? STL or stereolithography files are the most commonly used file format in 3D printing. The format was first introduced by 3D Systems in 1987. The STL file format is used to create a 3D model by representing its surface as a series of small interconnected triangles called facets. So in the figure, you can see the CAD model and the STL model. This is the STL model. You can see a series of small interconnected triangles, and these triangles are called facets. The facets are arranged in a way that makes it possible to recreate the surface geometry of the 3D model. The resolution of, so here this is the STL file of a face, of a human face, and here the last image, you can see the resolution is more. Why resolution is more? Because the number of triangles we are using is more. In the first figure, the resolution is less. Why? Because we are using less number of triangles. So the resolution of an STL file is determined by the number of triangles used to represent the surface of the 3D model. The more triangles used, the higher the resolution of the final 3D printed object. However, increasing the number of triangles can also increase the size of the file and slow down the printing process. One of the main reasons that STL files are so popular is their simplicity. The format is very easy to handle and can be read by most 3D printers and software. Additionally, STL files are lightweight and can be easily transferred between different devices and software applications. In summary, STL files are widely used in the 3D printing industry due to their simplicity, lightweight, and ease of use in 3D printers and software. The format is based on a series of interconnected triangles that represent the surface geometry of the 3D model, and the resolution of the file is determined by the number of triangles used. So coming to the product development cycle, because we are fabricating a product that is for the customer, so we should know the product development cycle to understand how we are going to prepare a product. The product development cycle is a crucial process that involves two main sections, that is virtual prototyping and rapid prototyping. In the initial stage, we need to define the product and prepare a concept design for evaluation. This involves understanding the product requirements, identifying the target audience who is going to use this product, and conducting market research. We should conduct a market research to determine the product's viability. Once the concept is finalized, we create a detailed design specification that includes all the product's features and functionalities. Next, we conduct design analysis to ensure that the product meets the requirements and specifications. This is an iterative process that involves testing and refining the design until it meets all the necessary criteria. We use advanced software tools to simulate the product's performance, identify any potential issues, and optimize the design for efficiency and effectiveness. Once we are satisfied with the design, we proceed to create a prototype. This involves using a range of techniques including 3D printing, CNC machining, and casting to create a physical model of the product. We test the prototype to ensure that it meets all the necessary criteria, including performance, reliability, and safety. Finally, we will document the 3D CAD model and design to ensure that all the product's features and functionalities are captured accurately. This documentation is critical for manufacturing, assembly, and quality control, and it provides a clear reference for future product development cycles. Then we will enter into the different concepts related to prototyping. Prototyping is a process of creating a preliminary model or sample of a product or system. It allows designers and engineers to test their ideas, experiment with different designs, and identify potential issues before investing time and resources in the final product. In the context of the car manufacturing industry, prototyping involves creating various types of prototypes to represent different stages of the design process. A virtual and rough prototype can be created by sketching a car design on paper or using software tools such as computer-aided design. Such a prototype can help visualize the overall design, identify potential design flaws, and refine the concept before moving to the next stage. The complete and virtual prototype is represented by the CAD model, which is a detailed and accurate 3D representation of the final product. It allows designers and engineers to simulate the performance, functionality, and interactions of various components and systems, and make necessary adjustments before moving to the physical prototype stage. The physical prototype is constructed using materials such as wood, plastic, or metal and represents the first physical manifestation of the design. It allows designers and engineers to test the design under real-world conditions, identify any issues with the design or materials, and refine the prototype before moving to the final stage. The final car represents the culmination of the prototyping process, where all the designs, components, and materials have been refined and integrated into a complete and functional product. It represents the physical, accurate, and complete expression of the design and is ready for mass production and commercialization. Then we will enter into the geometric capabilities. Additive manufacturing, it is again also known as 3D printing, has revolutionized the manufacturing industry with its remarkable geometric capabilities. Whatever whatever will be the shape of your geometry, maybe your geometry will be complicated, maybe your geometry will be very simple. Whatever be the geometry, we can fabricate it with the help of 3D printing technology. So 3D printing has revolutionized the manufacturing industry with its remarkable geometry capabilities. It allows us to create intricate and complex designs that were previously impossible to produce using traditional manufacturing techniques. With 3D printing, we can manufacture direct assemblies, which means we can create multiple components as a single piece, reducing the need for assembly and minimizing errors. Additionally, additive manufacturing enables us to produce conformal cooling channels, which are channels that are designed to follow the shape of the part, allowing for more efficient cooling and faster production times. Furthermore, the technology allows for mass customization, which means we can produce products tailored to the individual requirements without incurring high cost. One of the most impressive features of additive manufacturing is its ability to produce complex lattice structures. These structures are lightweight yet strong with unique properties that make them ideal for a variety of applications. Moreover, 3D printing has opened up the possibility of producing density-based functional grade materials. These materials have varying densities and properties within a single part, allowing for the creation of parts with optimized strength, flexibility, and weight. In summary, additive manufacturing is truly remarkable in its capabilities. It has transformed the manufacturing industry, allowing for the production of highly customized and complex parts with enhanced functionality. Then we will enter into the material capabilities. We already explained the geometric capabilities, such as whatever complexity is involved in the geometry, we can fabricate the physical product with the help of additive manufacturing technology. Coming to the material capabilities. Additive manufacturing is a process that involves creating three-dimensional objects by adding successive layers of material. This process can use a wide range of materials, including polymers, composites, ceramics, construction industry materials, biomaterials, food, pure metals, metal alloys, high entropy alloys, magnetic alloys, and functionally graded materials. Polymers and composites are popular materials in additive manufacturing due to their versatility and ability to create complex geometries. Ceramics are used for applications that require high temperature resistance. In the construction industry, materials such as concrete and plaster are used to create architectural models and prototypes. Biomaterials and food can also be used in additive manufacturing for applications such as tissue engineering and creating edible structures. Pure metals and metal alloys are used for applications that require high strength and durability, such as aerospace and automotive industries. High entropy alloys are a class of materials that have multiple principal elements, resulting in unique properties such as high strength and corrosion resistance. Magnetic alloys are used in applications such as sensors and actuators. Finally, functionally graded materials are materials that have a gradual change in composition, resulting in a gradual change in properties, which can be useful in applications such as thermal management. In summary, additive manufacturing offers a wide range of materials that can be used to create objects with varying properties and applications, making it a versatile and exciting field of technology. Then coming to the classification, ASTM classification. What is ASTM? ASTM is American Society for Testing and Materials. So they classified the additive manufacturing into 7 different categories. Okay, these are the 7 different categories based on American Society for Testing and Materials, that is ASTM. The first one is so ASTM is classified these seven technologies based on the energy consumption. So what photopolymerization is using less energy, whereas directed energy deposition is using the highest level of energy. So based on the energy consumption, ASTM is classified additive manufacturing into these 7 categories, such as what photopolymerization, material jetting, binder jetting, material extrusion, sheet lamination, powder bed fusion, and directed energy deposition. Thank you.